Hi-ho, in this video we're going to have a look at conditional probability, and I'll take you through a few steps to get there, so bear with me. Just as a quick recap of last video though, I just wanted to sort of point out that here we have a Venn diagram, and if we sort of broke it down into its individual components, we would see that this moon section would be A and not B. Okay, so it's all of A but not B, so it's just A and not B. This would be not A and B here. This is our classic intersection of A and B, and this would be not A and not B. Okay, so this would be how we would break it down. And note I'm using numbers here instead of probabilities. It's not but I could put P bracket around all of this kind of stuff and it would be the same thing. And I just wanted to just translate again back to the Carnot map, and you can see that here is where A and B exist, so this bit goes here. This is not A and B, so that would be this sitting here. This would be A and not B, which is this sitting here. And this, the bit outside the circles, is not A and not B. And do note, in a Carnot map, of course, we would total these up. Last example, I just gave probabilities in these different boxes, but they could be numbers as well. And it should always total up to the total amount in the sample space, or if it's a probability thing, then it should be totaling up to 1 or 100%, depending on how you're looking at. And just a reminder again, mutual exclusivity is when the number of elements in A and B, the number of outcomes in the intersection is 0, or the probability is equal to 0, either way, no overlap like we've got here. And a reminder of the probability addition rule here. Probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And because that's 0 when they're mutually exclusive, then it is sufficient to write probability of A union B is probability of A plus the probability of B. Now, you might want to think about what that means when you think about a weighted tree. And if you remember, we multiply across the branches and add down. What does that say about the events as they are represented in a weighted tree? Think about that. Here's another example. I won't spend too long on it because I have been through a few examples already. But here I'm given the probability of A union B being 0.7, the probability of B is 0.4. And I've said, what is the probability of A if A and B are mutually exclusive? So you can just use that second model where you've just got probability of A union B equals probability of A plus probability of B. You don't need the A intersect B bit. And then you can just solve quite simply to make probability of A equal to 0.3. Okay, that's just a bit of a recap, and now we're going to get on to the main part of the game, which is conditional probability. And the word you're looking for in a problem is often given. It's not always the word given. You might need to get it from different contexts, but often you'll see the word is given. So here's the example here. In a group of 20 people, 12 of them like Spider-Man and 14 of them like Aquaman. 2 of them like neither. So what we're going to do is we're going to construct a Venn diagram. I could have done a Carnot map, but I'll just stick with a Venn diagram. And then I'm going to lead you through some fundamental questions leading up to conditional probability to see how that works. Okay, so here's the Venn diagram here. Again, I strongly encourage you to pause the video and then fill it all out. Oops, I've actually got the answers here already, haven't I? I'm going to get rid of that so we can do it from scratch. So pause the video, fill out your own Venn diagram, then come back and we'll work on it together. Okay, so let's have a look at it. As you can see, I've got my Venn diagram already set up here with S for Spider-Man and A for Aquaman. And now I'm going to fill out the individual parts. I'll do it in a different color so we can sort of see it. So we're told that 12 of them like Spider-Man, 14 of them like Aquaman, and 2 of them like neither, and the total is 20. So we've got 2 out here, which means, I'll undo this in a second so that just as a quick note here, which means that there must be 18 between the 3 numbers here. Okay, so there's 18 in total. However, if you have a look at the numbers, you can see that if I look at the numbers here, I've got 12 of them like Spider-Man and 14 of them like Aquaman. So that's a total of 26. So if the Venn diagram is supposed to, or this bit, the circles, is supposed to represent 18, but in fact we've got 26, that means that there's an overlap of 8. So that must be the intersect, since the intersect is the overlap. So there's 8 in here. Okay, so what does that mean then for Spider-Man? If there are 12 people who like Spider-Man and 8 of them are represented in the intersection, then there are 4 left over here. And if 14 of them like Aquaman, but 8 of them are represented in the middle, then there must be 6 here, because 8 and 6 makes 14. And just to confirm, if I add them up, 4 plus 8 is 12, plus 6 is 18, plus 2 is 20, which is what's represented over here. Okay, code word for this video is Loki is the best. I'll say that again, key phrase really. Loki is the best. So moving on, we've now got a question. Why does it say question B? I don't know why. Oh, A was draw the Venn diagram. Okay, so I'm going to be doing a fair bit of flicking, between slides, because it's the way it's all broken up, but I'm sure you can cope. So here we go. A person is selected at random. What is the probability that the person likes Aquaman? Well, this is a pretty straightforward question, right? We're simply saying, what's the probability of Aquaman, A for Aquaman, and we know that we put it over the total number of possible outcomes, which is the 20 people who were surveyed. And then if we go back to our Venn diagram and have a look at it, we can see that there is a total of 14 people who like Aquaman. So that becomes the top number, 14 over 20, which is the same as 7 over 10. You can make it 0.7, you can make it 70%. There's no need to, unless you think it'll be useful. There's B done. C is given that the person. Oh, hang on. I'll just do. I don't know. I've done this from last year, or a couple of years ago when I've taught the course last. So, if you see me growling at the person who wrote this, it's actually me. What is the probability that the person likes both? Well, we can do the same sort of thing. We can go probability of what both would be A and S. It's going to be over 20 again, because that's who we're sampling from. But this time, we're looking at just the middle, right? These are the people who like Aquaman and Spider-Man. Aquaman or Spider-Man will be the whole lot. But this is Aquaman and Spider-Man, so it's the middle. So that's 8. And again, we can simplify that as much as we want to get our final answer. 2 out of 5 people like both. Okay, or to be more precise, it means if I selected someone at random from that group, what's the chances that I'll get someone who likes both? Well, there's a 2 in 5 chance, or a 40% chance that I'll pick someone who likes both. Now, D is where it gets interesting, and there's that key word given in there. Remember, it won't always be the word given, but it needs to have that kind of context. Given that the person likes Spider-Man, what is the probability that they like Aquaman? Or is it Aquaman? I think it's Aquaman. Okay, Aquaman. Okay, so given that the person likes Spider-Man, what does that kind of mean? I'll go back to my Venn diagram, and this is the representation of 20 people. Now, if I said given that they like Spider-Man, it's kind of like if I had 20 of the people in the room sitting down in front of me, I then said, okay, if you like Spider-Man, stand up. And then how many people would stand up? Well, these 8 would stand up because they like Spider-Man, and these 4 would stand up because they like Spider-Man. So the impact of asking that question, please stand up, is that I'm restricting my sample space. I've gone from 20 random people to 12 people who like Spider-Man. So I've restricted it from 20 down to 12, and that becomes my new sample space size, right? Because the other 8 people, I'm not even going to choose them. I know that they don't like Spider-Man. So given that they like Spider-Man, I now have 12. Now, what's the probability that when I pick someone at random from that 12, I'm going to get someone who likes Aquaman? What did you think? The answer is staring at you right in the middle there. These are the 8 people who would be still standing up from, being a Spider-Man liker, but also like Aquaman as well. So 8 out of the 12 would like Spider-Man, and that becomes our conditional probability. So I'll draw that up for us. So the probability, wait for the notation as well, the probability that they like Aquaman, given, and to represent given in a probability calculation, we're going to use a vertical bar like that. So probability that they like Aquaman, given that they like Spider-Man, is going to be 8 out of 12. 12, because that's all people who like Spider-Man. And 8, because they're people who like Aquaman. Oops, that should be a capital A. Who like Aquaman and Spider-Man. Okay, so that's basically how we do conditional probability. It's as easy and as hard as that. It can get trickier. I want to do it a bit more conceptually at this point, and I'm going to come up with a formula after I've done the conceptual stuff. So let's have a look at it. Basically, we can see that the intersection is going to be the collection that is common to both groups. We know that. And just for something that we're going to be doing later, please remember, or hopefully it makes sense, that A intersect B is going to be the same as B intersect A. They will be the same thing. Okay, so when I'm looking at the probability of A given B, like I've got here in this probability calculation here, really all I'm doing is I'm saying I'm restricting my sample space to the number of stuff in B, the number of outcomes in B. So I've got number of B as my bottom number instead of the total universal set. And if you think back to our example as well, the top number is always going to be the number of outcomes in the intersection, because this is not going to get a look in, and this is not going to get a look in as well, because they're still sitting down. So the only people I can draw from are these ones. So that's going to be the number of elements in terms of probability, the number of elements, or the number of outcomes, sorry, in A intersect B. And so this basically becomes our formula based upon numbers. But look at what I can do here. Now, this is a little bit of basic mathematics, but I'll take it slowly so you can sort of see it. I'm going to find an equivalent fraction. And you know that equivalent fractions are found by multiplying the top and the bottom of a fraction by the same number. And the number I'm going to choose deliberately is 1 over the universal set. And I will see what that does in a second. And I'm going to multiply the bottom by 1 over the number in the universal set. Okay, so what does that give us top and bottom? Do you remember what happens when we multiply a thing by 1 over? Basically, this becomes the top of the fraction. So the next line would be like this. Number in A intersect B over the number in the universal set, the total outcomes, over number in B over the number in the universal set, total outcomes. So here we've got one fraction that you should be able to identify. We can simplify that to a probability phrase. And here we've got another one. Maybe pause the video and think about it. What is that top part of the fraction called? What is the bottom part of that fraction? Don't say numerator and denominator. I mean, what probability does it represent? Did you get this? Hopefully you paused the video. The top part is just the probability of A and B. That's the basic definition. Probability of the event A and B must be the total number of outcomes matching A and B over the total outcomes. Similarly, down the bottom here, we've got the probability of B, because the top is the total number of outcomes matching just B, and the bottom is the total number of outcomes in the entire set. Okay, so that means that the probability of A given B can be calculated by going probability of A intersect B over the probability of B. like so. Now, just as an aside, and I'm going to summarize those in slide 15, but just as an aside, if I multiply both sides by the probability of B, then I'll have an expression for probability of A intersect B too. And that the probability of A intersect B must be the probability of A given B multiplied by the probability of B. Must be. I'll put a multiplication symbol in there just so you can see it. Okay, so that's just by multiplying both sides by probability of B. So in summary, the probability of A given B is equal to the probability of A intersect B over the probability of B. And the probability of A given B would be the probability, A and B, would be the probability of A given B multiplied by the probability of B. And you can use both of those calculations in order to solve some problems. I'm going to stop the video here because it's been long enough. In the next video, I'll go through a couple of examples.